What most people miss is not the rock itself, but how it reflects light under dust. A dull-looking stone with subtle vitreous luster or oily sheen often hints at a higher silica content or trace metals. When handled, it may feel heavier than its size suggests, a red flag for density anomalies. These subtle cues, weight in hand, light reflection, texture, are what separate ordinary rocks from potential gold or diamond hosts. The earliest differentiators are tactile and optical. A rock with a massive unbanded surface may look unremarkable until turned in direct light, revealing faint glints from sulfide grains or translucent quartz veins. Luster types matter. Earthy or waxy surfaces are rarely promising, but vitreous, glass-like, or greasy luster often points to quartz, chalcedony, or even jade. Similarly, adamantine sparkle, even when faint, can hint at microcrystalline inclusions like zircon or, in rare cases, diamond embedded in matrix. Another early clue is shape and grain. Angular, blocky fragments with no clear cleavage tend to resist weathering, characteristic of quartz and its variants. If a rock is granular but cohesive and the grains have interlocking boundaries, it may be a metamorphic host like amphibolite or serpentinite, both known to trap valuable veins or inclusions. Rounded grains loosely bonded suggest sedimentary rocks, which are less likely to trap primary value but might concentrate heavies downstream. Weight becomes diagnostic. Quartz, for instance, has a specific gravity around 2.65. If a rock of similar size feels like it weighs around 3 or more, there's a chance it carries sulfides like pyrite at 5, magnetite above 5, or jadeite 3.3 to 3.5. In the field, this weight-in-hand test isn't exact, but over time the experienced prospector learns to feel a false rock, one that shouldn't weigh that much unless something denser hides inside. Visual confusion is common. Rocks coated with iron oxides or algae films can conceal important features. A light water rinse or quick scrape with a knife edge reveals the true surface. If that surface has tiny crystals, fracture patterns, or hints of zoning, it's worth a closer look. Especially in quartz-rich systems, the presence of iron staining orange, brown, red often indicates hydrothermal action, a good sign. These stains appear where fluids moved through fractures, possibly leaving behind gold or heavy metal traces. Finally, knowing what not to chase saves time. Uniformly dull rocks with no luster changes, consistent low weight, or powdery weathering are rarely fruitful. Conversely, if a stone sparks the question, why is this heavier, shinier, or more granular than everything around it? That's the one to test. But knowing where to look, terrain, exposure, and transport paths matters just as much. In the next topic, we'll examine the geography of value, the landscapes that trap gold, quartz, and even diamond-bearing rocks before they're ever seen. It's not just what you find, it's where it stopped moving. Most gold-bearing rocks and diamond indicators don't sit where they formed. Instead, they collect in predictable traps, creek bends, slope breaks, and ancient riverbeds now dry and overgrown. These terrain features concentrate heavier material, separating potential value from the constant drift of lighter sediment. The simplest example is the inside bend of a stream. As water flows, its energy shifts, eroding the outer bank and slowing along the inner curve. That velocity drop causes heavy material like gold flakes, magnetite, and quartz nodules to settle out. Over time, these inside curves become natural sluices, storing pockets of enriched gravel beneath layers of ordinary wash. Even after surface flow disappears, the buried channel often remains a productive target. Another overlooked trap is the base of slope breaks, where a steep incline suddenly levels out. Material cascading down a ravine hits this flattening and deposits by weight. Larger, denser rocks fall out first. If gold-hosting quartz or serpentinite debris erodes from higher up, it'll likely concentrate in that catchment. A rock with iron staining or unusual density found here may have traveled meters, not miles, a clue to search uphill. Then there are paleochannels, ancient riverbeds that no longer flow. Often marked only by slight depressions, subtle soil color shifts, or aligned cobbles, these old waterways were once high-energy systems that sorted and dropped heavy material. They're especially critical in arid or glaciated regions, where surface flow has long since moved elsewhere. In places like parts of Western Australia, South Africa, or interior Brazil, some of the richest finds come from paleochannels buried under meters of silt. The war was lost. Berlin was ashes. Hitler was dead. But Reinhardt carried something the Reich could not afford to lose: not gold, not art, but documents, codes, and microfilm detailing networks that had burrowed deep into the post-war world. To the others, he was merely another officer seeking escape. To himself, he was the last custodian of an empire of secrets. The submarines slipped from the Norwegian fjord under a pale, deceiving moon. Around them, the Reich was crumbling into silence. Every radio transmission from Germany brought only despair, surrender, chaos, or vengeance. The captain, Oberleutnant Zur C. Heinz Schäfer, maintained the illusion of control, but his eyes betrayed fatigue. Every man aboard understood the truth. They were fugitives, not soldiers. They sailed westward into the Black Atlantic, a steel coffin adrift between the dying past and an uncertain future. For weeks the boat remained submerged, creeping through cold darkness to avoid Allied patrols. Men whispered of surrender, of safety in Argentina, of a life beyond the reach of Nuremberg. But Reinhardt's destination was different. He spoke little, kept to his bunk, and wrote in a small black journal bound in leather. It was rumored he possessed a contact in the United States, an industrialist sympathetic to the Nazi cause, waiting to extract him under a new identity. As the submarine crossed into mid-Atlantic waters, a quiet dread settled over the crew. Supplies dwindled, the batteries corroded with salt, yet Reinhardt's composure never faltered. He moved through the claustrophobic corridors like a specter, his face illuminated only by the faint red light of the control room. To some, he was merely an officer clinging to delusions of survival. To others, he was a man possessed by something darker, a mission that transcended defeat. The storm broke one night as they surfaced for air. Lightning cracked across the waves, revealing the monstrous solitude of the ocean. The periscope was retracted, the engines roared to life, and for a moment the submarine was no longer a tomb but a living beast defying the world's judgment. In that instant, Reinhardt stepped onto the deck, the rain slicing across his face. He closed his eyes, imagining the new continent that awaited him, the land of freedom, prosperity, and reinvention. He did not yet know that the sea itself had other intentions. The ocean, like history, forgets nothing. When dawn came, the U-boat disappeared beneath the waves once more, leaving behind no trace but a ripple on the gray Atlantic. Months later, in an age of peace and reconstruction, fishermen off the coast of Maine reported strange metallic echoes beneath their sonar. It would be decades before divers would descend into those depths and discover what truly lay entombed there, not just steel and bodies, but the final grotesque secret of a regime that refused to die quietly beneath the sea. The escape had succeeded in part, the officer had reached his destination. But what followed in the quiet harbors of America would unravel a different kind of war, one fought not with weapons but with silence, shadows, and memory. Transport also works against the unwary. Diamonds are hard but brittle, they fracture under pressure. This means long-traveled stones, especially in high-energy rivers, rarely survive intact. Instead, look near headwaters or glacial margins where erosion just began. Similarly, gold locked in quartz veins often appears in angular fragments near the source, gradually rounding as it moves. A jagged piece of rusty quartz pulled from a terrace may be closer to origin than its polished cousins downstream. In flat terrains, it's not always about where water flowed but where it stopped. Seasonal flood zones, known locally as wash flats or sheet wash fans, allow sudden, wide dispersion of water and deposition of heavies. These flats often reveal no surface sign, but beneath just 10 or 20 centimeters of overburden lie sorted layers of heavier rock. Reading terrain is about patterns. Clustering of heavy rocks in the wrong place, like uphill from a stream, signals human movement or artificial fill. But clusters within transport paths, especially if surrounded by nothing similar, mark potential hotspots. With the right tools, even a casual survey of terrain can reveal exactly where the hidden value collects. The first sign isn't gold, it's rust. More specifically, rusty streaks across pale quartz veins cutting through otherwise bland host rock. These iron-stained patterns are the residual fingerprint of hydrothermal fluids, hot, mineral-laden waters that once moved through fractures deep underground. Where they slowed, elements dropped out. First the iron, leaving hematite or limonite. Then, sometimes, fine-grained gold, invisible without magnification. Yet the rock still speaks if you know what to see. In the field, iron-stained quartz can appear orange, red, or brown, its hue determined by oxidation levels and mineral mix. What matters more is the context. If those colors streak through milky or translucent quartz and the host is competent, not crumbling, it's a potential auriferous system. Especially when the quartz appears in veins or stringers a few centimeters wide, branching across a few meters of exposed face. But color isn't enough. In isolation, iron-stained quartz might just be from iron-rich groundwater. What upgrades it to a clue is the company it keeps, especially sulfides. Tiny grains of pyrite, chalcopyrite, or arsenopyrite embedded in the quartz signal deeper systems capable of concentrating gold. With a hand lens, these appear as brassy specks or metallic flashes. Under sunlight, pyrite glitters sharply. Arsenopyrite has a more silvery luster with gray-black tarnish. If they cluster along fractures or contact zones, it's a better-than-average sign. Often, gold isn't visible even when it's present. In these systems, gold particles can be as small as 10 microns, less than 1/10 the width of a human hair, trapped between quartz crystals or bonded to sulfide grains. But the rock tells on itself. Crack open a stained quartz piece and look for vugs, small cavities or bubbles where mineral crystals once grew. These voids, especially if lined with druzy quartz or coated with iron oxides, signal a system that once had enough chemistry to concentrate metals. Another key detail is zoning. In hand specimens, zoning appears as color banding or texture changes. A piece of quartz with gradual shifts from clear to milky to reddish, all within the same vein, suggests fluctuating temperatures or fluid chemistry, ideal for multiple mineral deposition events. That complexity often accompanies gold. The risk is misreading iron-stained quartz as iron ore. Hematite or limonite veins without quartz rarely carry gold, and red rocks from laterite zones, common in tropical settings, may look promising but form from weathering, not hydrothermal action. A field knife test helps scrape the surface. If it powders easily into red dust, it's likely weathered laterite. If it reveals a translucent or hard quartz interior, it may warrant sampling. By now you're seeing a pattern. It's not just the rock, it's the relationship: luster, texture, stain, and host matrix. And these signs compound when you begin spotting associated green and black rocks that most mistake for trash, rocks that surprisingly hide jade and more. People step over it every day. Dull, greenish-black rock, sometimes with a waxy sheen, sometimes flaky and weathered. It looks like common waste. But in tectonic belts and subduction zones, this is often serpentinite, one of the most misunderstood and underappreciated rock types in the field. And it doesn't just host gold. In the right conditions, it becomes the parent rock of nephrite jade. Serpentinite forms when ultramafic rocks like peridotite undergo intense alteration through hydration. The result is a dense, often slick-feeling rock composed of minerals like lizardite, chrysotile, and antigerite. On the surface, it may present as dark green, nearly black, with a greasy luster. Some samples feel oddly soft under the knife yet refuse to break cleanly. This misleading texture hides what serpentinite can hold. In ancient orogenic belts, places where continents collided, serpentinite zones often host narrow quartz carbonate veins. These veins may carry visible pyrite, arsenopyrite, or even native gold in trace amounts. But more frequently, the value lies deeper, locked in metamorphic history. When these rocks undergo additional pressure and low-grade metamorphism, tremolite and actinolite crystals begin to grow, aligning into dense, fibrous masses, nephrite jade. Nephrite is heavier than most expect. With specific gravity around 2.9 to 3, a hand-sized sample weighs significantly more than a similarly sized piece of quartz. Its fracture is splintery or fibrous, not granular, and it resists breakage under force. In the field, most people discard it as hard soapstone or think it's just polished river cobble. But when polished, true nephrite reveals an interlocking, silky texture and deep green translucency. Key field signals include the presence of epidote bright pistachio green, chlorite soft dark green powdery coating, and actinolite shiny needle-like fibers in cross-sections. When found together, these minerals mark a zone that experienced the right temperature and pressure window for jade formation. And serpentinite exposed in shear zones, especially near tectonic boundaries like those found in British Columbia, New Zealand, or southern Brazil, often carries this sweet. The main danger is misclassification. Soapstone, talc schist, and even some altered basalt can mimic serpentinite. A simple field test helps: scrape the rock with a steel knife. If it powders easily and feels greasy, it may be talcrich. If it resists and the surface polishes under pressure, serpentinite is more likely. Add water. If the rock darkens but retains a waxy sheen, it's a good sign. In many countries, jade-bearing serpentinite belts have triggered mining rushes. Yet much nephrite remains hidden in unremarkable outcrops because it lacks crystal faces or flashy surfaces. Only those who know what to look for: weight, resistance, fiber orientation, pull value from it. And sometimes what appears in that serpentinite belt isn't jade or gold at all, but something even rarer: a broken nodule of kimberlite eroded from pipe to pebble. and those pieces look like nothing special unless you know the texture. Most mistake it for cement debris or river-worn slag, a dull bluish-green rock with no sparkle, no symmetry, and a gritty, fibrous interior. But this is weathered kimberlite, one of the only primary sources of natural diamonds on Earth. When fresh, it's soft, clay-like, and easily broken. When altered and moved, it turns into rounded, compact nodules that people kick aside without a second glance. Kimberlite is a volcanic rock that erupts from deep in the mantle. It travels fast, tens of kilometers per hour, bringing with it high-pressure minerals like pyrope, garnet, ilmenite, chromite, and sometimes diamonds. But once it reaches the surface, weathering begins almost immediately. Rain, oxidation, and temperature swings break down the feldspar and olivine, turning the once solid rock into a friable, dusty mass. In dry climates, this creates surface crumbles that resemble compacted ash. In wetter zones, it leaves behind soft, greenish clay with embedded pebbles. The key to spotting it is texture. Weathered kimberlite often looks like nothing, just a smear of green-gray against the soil. But when broken open, it reveals a fine-grained, matrix-rich interior, sometimes speckled with black or brown grains. These grains can be chromite or ilmenite, both of which are dense, metallic, and magnetic, an important trio of traits for field identification. A magnet sweep is the fastest first filter. Run a small neodymium magnet across broken pieces. If black grains jump or stick, that's a strong hint. Ilmenite and magnetite respond well, chromite less so, but it's still heavier than surrounding material. Once identified, those grains should be isolated and inspected under a loupe. Look for subhedral crystal shapes, metallic luster, and dark gray to black color without obvious cleavage. These are hallmark indicators that, while not valuable on their own, signal proximity to a kimberlite source. Where these rocks appear matters. In known diamond fields, Central Africa, Siberia, parts of Canada, and Brazil, kimberlite pipes have weathered for millions of years, releasing their load into nearby river systems. As the soft rock breaks down, diamonds and indicator minerals migrate, but they don't go far. Diamonds are heavy for their size, specific gravity near 3.5, and tend to drop quickly. Most travel less than 1 kilometer from source. Finding a rounded nodule with kimberlite texture in a streambed may be the only above-ground clue to a buried pipe uphill. The risk is confusion with man-made material. Weathered concrete or furnace slag can mimic the look of altered kimberlite, but slag usually contains sharp metallic fragments and bubbles, whereas kimberlite breaks dull without glassy sheen or hollow voids. A hardness test helps. Kimberlite is soft, often below Mohs 4, and can be scratched with a copper coin or steel nail. When confirmed by texture, weight, and magnetic response, a weathered kimberlite nodule becomes more than a curiosity, it becomes a directional tool, because where one fragment is found, others usually follow, and hidden among them may be the true targets, garnets and spinels that act as signposts, pointing to something much harder to see. And that's where testing begins. The beauty of a first-pass field test is that it costs almost nothing, and yet it can save weeks of wasted effort. The right 3 tools, a magnet, a steel nail, and your own hand, can quickly separate common rock from possible host material for gold, quartz, or diamonds. These tests don't confirm value, but they eliminate noise. And in the field, efficiency is everything. Start with weight in hand, pick up the candidate rock and compare it to others of similar size nearby. If it feels notably heavier, that's a density flag. Quartz averages 2.65 in specific gravity. Serpentinite and nephrite land closer to 3. Ilmenite and magnetite climb above 4.5, sometimes over 5. And if gold is present, especially within sulfide-streaked quartz, the difference is even more pronounced. No scale is needed. Your hand adjusts quickly to local baseline weight, and anything heavier becomes suspect. Next, apply the magnet. A small neodymium magnet easily carried on a keychain or pocket clip reveals ferromagnetic minerals instantly. Magnetite responds strongly. Ilmenite reacts weakly but noticeably if isolated. These minerals aren't valuable themselves, but they're part of key indicator suites, especially near kimberlite or gold systems. Run the magnet across broken surfaces, not weathered rinds, to avoid false negatives. If the magnet picks up multiple grains or the entire rock jumps slightly, it's worth a closer look. Then comes the scratch test. A basic steel nail rates about 5.5 on the Mohs scale. Use it to score the surface of the rock. If the material scratches easily, it's below that threshold, possibly weathered kimberlite, serpentinite, or soapstone. If it resists or sparks under pressure, it could be quartz-rich chalcedony or even host to microcrystalline silica. Sharp resistance, especially if accompanied by a slight ring when tapped, suggests something worth isolating. Combine all 3 tests for better resolution. For example, a dull greenish rock that feels heavy, scratches easily, and responds weakly to a magnet might be serpentinite or nephrite-bearing material. A light-colored rock with fine-grained black specks, no magnetic response, and hard surface might be quartz with embedded sulfides or even a misleading zircon-rich matrix. A clay-coated fragment that crumbles in hand but releases dense magnetic grains when crushed could be decomposed kimberlite. These early reads shape where you spend time. If a zone yields multiple magnet-positive samples with high density and scratch resistance, it's a candidate for sieving or gritting. If the rocks show none of these signs, it may be time to move on. The goal isn't to prove value yet, it's to filter down the field. Quartz fools more people than any other mineral. It's everywhere, found in veins, nodules, and fragments across most terrains. But only a fraction of it signals value. The rest is dead weight. The problem is that promising quartz doesn't always look special. In fact, some of the best samples appear dirty, fractured, or downright unattractive. It's the internal context that matters. The first illusion is color. Many expect valuable quartz to be crystal clear or at least translucent. In reality, milky quartz, opaque and white from microinclusions, is often a better host for gold. That's because it forms in lower temperature hydrothermal systems where gold precipitates along with silica and iron. These systems don't make pretty crystals. They make saturated iron-stained blocks with little visual appeal. But not all milky quartz is useful. The key is association. If the quartz is intergrown with sulfides, especially pyrite, galena, or chalcopyrite, it deserves testing. Under magnification or strong light, look for tiny metallic specks along fractures or boundaries between crystal zones. These specks are often brassy, sometimes iridescent, and can appear reddish or greenish under oxidized surfaces. If found, they signal mineralizing fluids moved through that system, fluids capable of depositing gold. Another important signal is vug development. Vugs are cavities left behind when gases or fluids escape during formation. In quartz, they often form lined chambers filled with tiny needle-like crystals or iron oxides. Their presence means the system had dynamic chemistry, an environment where multiple mineral types could precipitate. If those vugs are rimmed with limonite or other oxides, they often hosted sulfides first. Gold, in some cases, occurs as fine-grained flecks in these spaces, locked inside or adjacent to secondary iron minerals. Quartz habits also matter. Massive quartz, solid, uncracked blocks rarely contain much of interest. In contrast, brecciated or shattered quartz, especially if healed with later silica or carbonate, tells a story of multiple fluid events. These are ideal for trace gold deposition. A rock showing angular quartz fragments in a matrix of darker material may have hosted repeated fracturing and resealing, each stage introducing new mineral load. Texture is another clue. Greasy or waxy quartz, often chalcedonic or cryptocrystalline, forms under different conditions than glassy, sharp-edged varieties. This waxy luster, especially in banded agates or jasper-like material, can signal low-temperature silica saturation, good for hosting other elements if nearby systems contributed. But the biggest trap is sparkle. Some quartz glitters on the surface because of mica flakes or surface tension from moisture, not because of value. Visual brilliance without substance. Test it. Real sulfide-bearing quartz will respond to a magnet sweep via included minerals, a weight-in-hand check often heavier than average, and sometimes even a UV light test if secondary minerals like scheelite or fluorite are present. It gleams in the pan, it flashes under sunlight, but it's not gold and it's not diamond. It's fool's quartz, glassy, brittle, and worthless, or zircon, hard, heavy, and misleadingly brilliant. These false positives waste more time than poor geology. They lure prospectors with sparkle but break under test. Learning to unmask them isn't optional, it's essential. The most common offender is mica, especially muscovite or biotite flaked off from schists or gneiss. It appears in pans, riverbeds, and decomposing bedrock as paper-thin reflective plates. It looks like silver or gold until touched. A finger swipe scatters it. Under a loupe, it shows as flexible, transparent, or black sheets, often arranged in cleavage stacks. It weighs next to nothing. If it floats or moves easily in water, it's not gold. True gold hugs the bottom of the pan, heavy and reluctant to shift. Then comes zircon. Unlike mica, zircon is genuinely dense, around 4.6 in specific gravity, and very hard, approaching 8 on the Mohs scale. It can resemble small diamonds or sapphires depending on color and clarity. Many zircon crystals are prismatic, with sharp edges and a high refractive index. But they're not rare and they're not worth much unless cut and flawless. Worse, in kimberlite regions, zircon often appears alongside indicator minerals, causing confusion. A prospector might think zircon is proof of diamonds nearby. It is. On its own, zircon is a false lead. One way to test is through facet doubling. Under a 10x loop, zircons can show doubled facet edges, an optical signature absent in true diamonds. Additionally, while both zircon and diamond may fluoresce under ultraviolet light, zircon often shows yellow or orange fluorescence, while most natural diamonds show a weak blue. Still, fluorescence is not diagnostic alone. Another misleading mineral is corundum, especially low-grade sapphire. It's hard, non-metallic, and occurs in metamorphic terrains that also host jade or garnet. When tumbled in rivers, it appears as dull, rounded pebbles, but when fractured, reveals a high-gloss interior. Its hardness, 9 on the Mohs scale, means it resists steel but not diamond. Many mistake it for high-value gem rough, but most natural corundum is too flawed or opaque for cutting. Glass and high-index simulants are a modern issue. In some regions, especially near old mining sites or artisan markets, glass fragments are introduced into streams to seed value. These fakes pass casual inspection but fail field tests. Glass scratches at 5.5 to 6 and shatters under pressure. It lacks cleavage, has conchoidal fracture, and often shows trapped bubbles. Under loupe or microscope, the difference is stark. The best defense is consistency. A test suite, weight in hand, hardness check, magnet sweep, and visual under loupe filters nearly every false lead. If one indicator points to value but others don't confirm, it's a red flag. Real mineral systems produce clusters of clues: weight, texture, companion minerals, and resistance to breakdown. False positives shine alone, without context. When visual tests reach their limits, the serious work begins, not with a lab but with a compact, upgraded field kit. Classifier sieves, ultraviolet light, and thermal conductivity pens can transform a bucket of random rock into a clean concentrate of candidates. These tools don't confirm value outright, but they sort the noise from the signal fast enough to decide what to carry out and what to leave behind. Start with classification. A simple stack of classifier sieves, typically mesh sizes 20 and 40, lets you separate out the most promising size fractions. 20 mesh captures particles around 0.85 millimeters. 40 captures down to about 0.42. This matters because gold, magnetite, garnet, and diamond indicator minerals often concentrate in that narrow size band. Too large and you're carting host rock. Too small and it's dust with no economic value. After screening, focus your effort on the heavies retained in the 20 to 40 window. Next, introduce ultraviolet light. A portable long-wave UV flashlight, preferably rated at 365 nanometers, can reveal fluorescence in a variety of field minerals. Diamonds, if present, often fluoresce blue to bluish-white, but so do some common materials like calcite or fluorite. That's why context is critical. A lone fluorescing pebble might be worthless, but if it shows adamantine luster, high hardness, and sits among indicator minerals like pyrope, garnet, or ilmenite, it deserves attention. Even more decisive is thermal conductivity. A diamond tester, widely available and no larger than a marker, uses heat flow to distinguish diamond from simulants. Touch the probe tip to a clean surface. Diamond will dissipate heat almost instantly, triggering a positive read. Moissanite, however, can mimic this behavior, so the tester must also check electrical conductivity. True diamond is electrically insulating. Moissanite conducts slightly. Units with dual modes eliminate false positives quickly. These tools are mobile. A foldable classifier, a UV penlight, and a pocket tester weigh less than a kilogram and can screen dozens of samples in an hour. They won't replace full lab work, but they narrow the field. For example, a candidate rock may show no magnetism, high density, no fluorescence, and pass thermal, suggesting quartz, possibly with inclusions. Another may glow under UV, conduct heat fast, and sit among chromite and pyrope grains. That one earns a sample bag and label. The risk is overconfidence. None of these tests alone prove value. Some synthetic materials, especially modern diamond simulants, will pass several tests. But in the field, when samples are fresh, dirty, and uncut, the combination of physical separation and fast response screening builds a layered profile. It's not about certainty, it's about making smarter choices with every step. Field success doesn't come from luck, it comes from repeatability. When a sample shows promise, the ability to return to that exact spot and replicate the find is what separates a one-off curiosity from a viable lead. That's why establishing a sampling grid, even a simple one, is the next critical move. Without it, you can't trace concentration patterns, identify vectors, or legally support a claim if it comes to that. The process begins with baseline marking. Use a handheld GPS, phone app with offline maps, or even a topographic printout with coordinates to anchor your starting point. Mark it physically, flag tape, stone cairn, or metal tag on a tree. From there, lay out a grid, either in fixed intervals like 10 meters by 10 meters, or adaptive to terrain features such as slope, water access, or visible rock formations. At each grid point, extract a controlled sample, roughly 1 to 2 kilograms of material. If dealing with stream sediment, keep wet and dry samples separate. Label each clearly with location code, date, and grid reference. Use durable, waterproof tags or directly write on sample bags. This prevents the classic mistake, promising concentrate with no way to trace it. Photograph every sampling site. A wide-angle overview and a close-up of the exact dig zone ensure future reference, especially if foliage changes or erosion alters the site. Include a visible scale like a coin, pen, or measuring tape to provide context. Record conditions. Ambient temperature, recent rainfall, water clarity, slope gradient. These influence both sample content and ease of replication. For example, a heavy rain 2 days prior might have washed an upstream float, giving a false impression of local mineralization. By logging weather and environmental context, you can sort anomalies from trends. After sample collection, concentrate the material with classifiers or pans and repeat your field tests: magnetism, weight, UV, and hardness. Record results at the source, not later. Inconsistencies in sample behavior often point to movement. A gold-bearing quartz fragment far from its host vein, or a kimberlite pebble in alluvial tailings. Use a simple chart, grid square, sample weight, retained heavies, visible indicators, test outcomes. Over a dozen or more points, patterns emerge. Maybe garnets cluster in one quadrant. Maybe UV-positive fragments show up only below a certain slope break. These aren't just observations, they're guides. The grid becomes a map of probability. In professional exploration, this stage is called Phase 1 prospecting. It's low cost, high efficiency, and lays the foundation for any follow-up. And when findings lead to a contradiction, like a high-value rock that doesn't match the local geology, it sets up the twist. The best-looking rock in the bag doesn't always belong. It might hold dense mineral grains, pass the scratch test, show pyrope or ilmenite, but something feels off. It doesn't match the others from the grid. When a sample's composition contradicts the known geology of the area, you may be facing a float, a displaced fragment that drifted from its origin. Or worse, you may have uncovered a mistake that resets your whole field model. The moment of doubt usually comes post-concentration. A single sample lights up the thermal pen, responds weakly to a magnet, and shows a greasy luster underwater. It fits every marker except the terrain. For example, you're in a zone dominated by sedimentary sandstone and shale, with no mapped ultramafic or volcanic structures. And yet the sample feels like a piece of altered lamproite or kimberlite. How? The answer lies in transport. Many rocks don't stay put. Glacial action, landslides, and high-energy floods can move dense materials great distances. In regions with glacial history, like northern Canada, Scandinavia, or parts of the Andes, boulders from hundreds of kilometers away rest in unexpected terrain. These are glacial erratics, and their presence can mislead even experienced geologists. To verify a float, return to the grid and intensify sampling around the discovery point. If no similar material appears within a 10 to 15 meter radius, and other grid points yield nothing matching its texture, weight, or mineral profile, it's likely transported. Another indicator is wear. Floats that traveled far often show rounded edges, abraded surfaces, and oxidation patterns inconsistent with local weathering. They may be coated with foreign soils, clays, or algae types not found in the current streambed. A proper mineral ID test clinches the puzzle. Send the rock for lab spectroscopy or portable XRF analysis if available. The results might show high chromium, magnesium, and titanium values, traits of kimberlite or lamproite, but no regional match. That means it didn't form here. It drifted, and now you're not chasing a vein or a pipe, you're chasing a trail. This reversal changes strategy. Instead of intensifying local sampling, the focus shifts upslope or up glacier. Map the likely movement vectors, prevailing glacial direction, slope gradient, historic water flows. In mountainous terrain, gravity rules, fragments rarely travel uphill. In glaciated zones, consult moraine data, erratic distribution maps, and known ice flow directions from geological surveys. Sometimes the float is a breadcrumb from a rich source buried just out of sight, like a small kimberlite exposure masked by overburden. Other times it's a decoy leading nowhere because the original pipe lies 50 kilometers away. But either way, identifying the float forces you to recalibrate. It protects you from drilling or pitting the wrong location, and opens the door to a much bigger find if the trail holds. Before a diamond ever sees daylight, its path begins with indicators, tiny mineral scouts that survive the journey better than the gem itself. Pyrope garnet, ilmenite, chromite, and spinel form the mineral suite that points the way to kimberlite or lamproite pipes. In many cases, these grains are found long before any diamond. And if you know how to read them, they draw a map far more precise than guesswork. Pyrope is the most famous of the diamond indicators. A deep purple to reddish garnet with a high chromium content, it's denser than common garnet species and often survives erosion well. In the field, it appears as a rounded, glassy grain, sometimes angular, depending on distance traveled. Under magnification, its color saturation and internal zoning can be seen, often with a dark core and translucent rim. It doesn't respond to magnets, but its weight and luster are distinct. Next is ilmenite. Dense, black, and weakly magnetic, ilmenite often appears as granular blebs or flattened grains in stream concentrates. Its specific gravity hovers around 4.7. A magnet sweep helps isolate it, especially after sieving to the 40 mesh range. Ilmenite is important not just as a pathfinder, but also because its chemistry, especially titanium and magnesium levels, helps assess the fertility of the source kimberlite. Fertile pipes tend to produce ilmenite with certain chemical ratios, often analyzed in lab settings. Chromite is another key player. Typically black or very dark brown, it appears submetallic and lacks clear cleavage. It is heavier than ilmenite and non-magnetic, helping distinguish it during concentrate work. In diamondiferous systems, chromite often forms as part of a trio with pyrope and ilmenite. When found together in a stream trap zone, say at the base of a gravel bar or behind a boulder, it suggests a local, eroding kimberlite source. Spinel, while not exclusive to kimberlite, adds detail to the indicator profile. In diamond exploration, magnesian spinel with high chromium is a positive sign. It typically appears as small, octahedral crystals with good luster and high durability. Found in high-energy settings, spinel may survive transport better than garnet. Its presence, especially alongside other indicators, adds confidence to a float trail or erosion fan. These minerals don't travel far from source. Most studies show that 90% of indicator minerals settle within 5 kilometers of their origin. In high-energy terrain, steep, fast-moving creeks or glacial till the range extends slightly. But generally, when you find multiple indicators in one area, the pipe or dike is close. The exception is when minerals are reworked into secondary deposits, older gravels or terra systems, where they accumulate over millennia. In practice, the workflow goes like this. Concentrate stream sediment with classifiers and a sluice or pan. Magnet sweep the result, isolating magnetite and ilmenite. Visually scan for glassy red grains, pyrope, and dark, dense fragments, chromite. Document the find location precisely. Repeat at intervals upstream. When the indicators disappear, you've passed the source. Not all ground tells the same story. Some terrains are rich with indicators and host rocks, others are geological deserts for high-value minerals. Knowing where the system works and where it doesn't prevents wasted time and misread signals. Regional geology sets the rules. Without it, even the most advanced test suite will lead you in circles. Diamond indicators, for example, require specific source rocks, kimberlite and lamproite. These volcanic intrusions form under stable continental cratons, thick, ancient pieces of Earth's crust. That's why diamond exploration is productive in regions like the Canadian Shield, the Kopval Craton in southern Africa, the Siberian Craton, and portions of Western Australia and central Brazil. Outside these zones, even a perfect pyrope grain is likely a fluke or a secondary redeposit, meaning the pipe is long gone or never existed. In contrast, jade, both jadeite and nephrite forms in dynamic high-pressure zones. Nephrite originates in serpentinite bodies, often along faulted or subducted boundaries. These appear in mountain-building belts, the Pacific Northwest, parts of Central Asia, southern China, New Zealand, and Chile. Jadeite, the rarer of the two, forms at even higher pressures and is typically restricted to subduction complex terrains. That's why it's tightly associated with Myanmar, Guatemala, and specific belts in Japan and California. Searching for jadeite in shield regions, where pressure conditions were never sufficient, is futile. Gold, however, is more flexible, but still follows patterns. The richest lode gold deposits form in greenstone belts, which are Archean to Proterozoic volcanic sedimentary complexes. These exist in places like the Yilgarn Craton of Western Australia, the Abitibi Belt in Canada, and parts of West Africa. Gold also concentrates in hydrothermal quartz veins, often in structurally deformed zones or contact metamorphic settings. But placer gold, free gold in rivers, requires both upstream lode sources and active or ancient water systems. Dry regions without historical flowpaths yield little, even if gold once formed there. This regional filter also applies to false positives. For example, zircon is ubiquitous in high-grade metamorphic terrains. Finding it there proves nothing about diamond potential. Similarly, garnet is common in schists and gneisses unrelated to kimberlite. Without the right context, a deep red grain is just another garnet, not a pyrope. Another trap lies in lateritic zones, especially in tropical environments. Iron-rich crusts formed by extreme weathering often mimic the look of mineralized veins or gossans, yet they're usually barren, residues of leached rock with no remaining metal. In parts of Southeast Asia and Central Africa, prospectors waste entire seasons chasing these ghosts. Using this geographic lens means adjusting methods by region. In craton zones, focus on heavy mineral concentrates and indicator suites. In subduction belts, prioritize serpentinite exposures and metamorphic textures. In gold terrains, follow quartz vein systems, especially those with iron staining and sulfide trails. Each rock type, each signal, has a habitat. Mapping isn't optional, it's foundational. Before fieldwork begins, overlay regional geology maps, satellite data, and known resource zones. Public geological surveys, often run by universities or state agencies, provide detailed fault lines, intrusive bodies, and mineral occurrence reports. Align your sample grid not just with terrain, but with geologic possibility. The best ground is often the most dangerous. Rich exposures lie along steep ravines, undercut streambanks, or remote highlands where few venture, not just because it's hard, but because it's risky. Working in these areas requires more than geology. It demands situational awareness, timing, and respect for natural and legal boundaries. Miss any one of these, and even a perfect sample isn't worth the cost. Flood zones are the first threat. In gold-bearing river systems or kimberlite-bearing creek beds, the richest deposits often sit just beneath low banks or within meander traps. But these same locations can become deadly during sudden rain. Especially in tropical regions or mountainous terrain, water levels can rise by over a meter in less than 30 minutes, turning a productive bend into a torrent. Always scout upstream weather, even if the sky overhead is clear. Portable radios, satellite messengers, or even simple weather apps can make the difference between a productive day and an emergency extraction. Then there's slope danger. Serpentinite belts, known hosts for jade and gold, often appear on unstable hillsides where rock has decomposed under tectonic strain. These slopes shear easily underfoot and expose serpentinite weathers to slick, clay-rich soil. Footing is deceptive. A ridge that feels solid in the morning may slump by late afternoon, especially if moisture seeps through joints. Rope systems, climbing gear, or at minimum a buddy system, are mandatory in such conditions. Many field geologists mark high-risk zones with biodegradable flagging to avoid repeat entries under unstable overhangs. Wildlife adds another layer. Remote jade or gold zones often overlap with bear habitat in North America, jaguar range in South America, or venomous snakes in Asia and Africa. The risk isn't just attack, it's disruption. A startled animal can trigger rockfall, flush loose soil, or simply make a narrow path unusable. Carrying deterrents, noisemakers, or having a visual scout ahead of sampling zones becomes routine in known wildlife corridors. Legal access is a quieter but equally serious danger. In many regions, mineral rights are severed from surface rights, meaning that even on public or communal land, collecting without a permit can lead to seizure of samples or legal action. Some zones fall under indigenous stewardship or are designated conservation areas with strict no-collection rules. Before any sampling, always consult land records, forest access permits, or regional mining databases. In Brazil, for example, areas within 5 kilometers of indigenous reserves are typically off-limits. In Canada, many high-grade kimberlite belts fall under protected or leased territory with enforced claims. Then there's the window. Seasons dictate everything. Alpine jade belts may only be accessible for 6 weeks per year, when snow melt stabilizes but before fall storms close roots. Tropical diamond fields often become unreachable during wet season due to mud, washed-out roads, or contaminated water. Planning access within these natural windows isn't optional. It defines whether work can happen at all. This risk profile shapes sampling. It's why light gear, small-volume test runs, and advanced reconnaissance are standard. Carry only what's essential: classifiers, magnet thermal tester, UV pen, sample bags, GPS, safety kit. Leave bulk behind until a location proves repeatable and rich. Work in pairs or trios. Notify someone off-site of your exact plans, return times, and fallbacks. A rock that passes visual and field tests still isn't confirmed. Real verification begins when its physical properties are measured precisely: thermal conductivity, electrical resistance, and specific gravity. These tests, while simple in principle, expose truths no hand lens can see. They separate lookalikes, validate indicators, and guide whether to invest further or walk away. Thermal conductivity is the primary non-destructive test for suspected diamonds. Diamonds conduct heat extremely well, far better than glass, quartz, or cubic zirconia. A handheld thermal tester uses a fine probe to deliver a small pulse of heat to the surface. If the material dissipates that heat nearly instantly, it registers as a diamond. But moissanite, a synthetic used to mimic diamond, also conducts heat efficiently. That's why advanced testers include electrical conductivity. Diamonds are electrical insulators, moissanite conducts. When both tests agree positive thermal, negative electrical, the result is highly reliable. For jade and other dense stones, specific gravity tells the deeper story. This test compares the weight of a sample in air versus its weight in water, using Archimedes' principle. Jadeite typically has a specific gravity between 3.3 and 3.5. Nephrite lands between 2.9 and 3. Most fakes like glass or dyed resin fall under 2.6. Even a crude water displacement test using a scale and graduated cylinder can reveal the truth. For accuracy, the stone must be clean, fully submerged, and free of bubbles. Electrical resistance adds another layer, particularly for quartz and metallic sulfides. Many sulfide-hosted gold specimens, especially those with pyrite or chalcopyrite, conduct weakly due to metal content. Quartz, in contrast, is a strong insulator. When paired with weight, magnetic response, and visible inclusions, resistance measurements help build a material profile consistent with known ore types. Some testers also offer reflectivity and UV response modes. Under long-wave ultraviolet light, certain minerals fluoresce distinctively. Natural diamonds often glow pale blue, though some fluoresce yellow or green depending on nitrogen content. Synthetic simulants like cubic zirconia may show strong fluorescence, but with unusual colors, another useful clue. Jade, depending on impurities, may show dull cream or faint green fluorescence, though not consistently. These physical tests are inexpensive compared to full lab assays but reveal much. A stone that looks right but fails gravity is likely a fake. A dense magnetic fragment with no UV and low conductivity might be magnetite, not ilmenite or chromite. A pyrope-colored garnet that sinks like glass and lacks thermal response probably isn't from a kimberlite suite. Document every test, the readings, tools used, and conditions. This builds a sample dossier that supports any later certification or sale. For high-value candidates, it also informs which ones justify a full laboratory assay, costing anywhere from a few hundred to several thousand, depending on material type and detail required. Not all discoveries pay. Some just glitter, others, under the right market conditions, become worth thousands per gram. The difference isn't just the material, it's the intersection of quality, origin, and current demand. Whether gold, jade, quartz, or diamond, raw stones fall into distinct value bands that the market recognizes. Knowing which band your sample fits into determines whether it's worth cutting, selling rough, or holding for provenance-based premiums. Take gold. Pure native gold commands value by weight, measured in carats and fineness. In nugget form, market value aligns with spot price, currently hovering around $60 per gram or roughly $1,800 per troy ounce. But visible gold locked in quartz can exceed that, depending on specimen quality. High-contrast gold in white quartz, especially with dendritic patterns or multi-gram mass, can fetch 2 to 5 times bullion value from collectors. A 2-gram specimen might sell for over $300 if the matrix is clean and the form aesthetic. Jade splits sharply by type. Nephrite jade, more common, ranges in value from $10 to $100 per kilogram in rough form, unless translucent and apple green, which climbs to $500 or more per kilogram. Jadeite, by contrast, starts higher. Untreated imperial green jadeite with fine grain structure can reach thousands per kilogram even in raw state. A tennis ball-sized piece of high-grade jadeite may auction for $5,000 to $20,000 depending on color, saturation, translucency, and origin. Burmese material still dominates the top of this market, though Guatemalan and Japanese sources have rising demand. Quartz is trickier. Most is valueless in bulk, but exceptions include collector-grade smoky quartz, amethyst, and rutilated quartz with visible inclusions. These may sell from $20 to several $100s per specimen if undamaged and well-formed. Quartz with visible gold becomes far more valuable, as noted. So does quartz hosting rare sulfides or forming unique textures, botryoidal pseudomorphs, or unusual growth habits. Diamonds are the most extreme in price variance. Industrial-grade stones used for abrasives might sell for less than $2 per carat, but gem-quality rough clear octahedral over half a carat can command $100 to $500 per carat uncut. Larger or flawless rough jumps exponentially. A 2-carat clear well-formed octahedral diamond may fetch over $5,000 uncut. Fancy colors, like yellow, pink, or blue, increase this tenfold depending on hue strength and saturation. Origin adds further premiums. Canadian and Botswanan diamonds with ethical chain of custody can price higher than similar stones from less regulated sources. These numbers depend on verification. No buyer pays premium without proof. This means third-party certification, labs like GIA, IGI, or local geological institutes, who confirm not only mineral identity but treatment status and origin when possible. That process costs, often starting at $100 per stone. So knowing which samples merit that investment is key. It's here that fraud creeps in. Sellers know which traits push price bands, and many manipulate stones dyed jade, assembled quartz, lab-created diamond, passing them as natural. The next step then is protection. How do you avoid getting lowballed, or worse, fooled into believing a worthless stone is a rare find?